Hi, here we are discussing spectral series in atomic spectra. The light emitted by a particular element would exhibit some regular pattern. Hydrogen is the simplest atom, therefore has the simplest spectrum. In the observed spectrum, however, at first sight, there does not seem to be any resemblance of order or regularity in spectral lines, but the spacing between lines within certain sets of hydrogen atom decreases in a regular way. Each of these sets is called a spectral series. In 1885, the first such series was observed by a Swedish schoolteacher, Johann Jacob Balmer, in the visible region of the hydrogen atom. This series is called the Balmer series, as shown in the figure. The line with the longest wavelength, 656.3 nanometer, in the red is called H alpha. The next line with the wavelength 486.1 nanometer in the blue green is called H beta. The third line 434.1 nanometer in the violet is called H gamma, and so on. As the wavelength decreases, the lines appear closer together and are weaker in intensity. Balmer found a simple empirical formula for the observed wavelength as shown in this. This equation shows 1 by lambda is equal to r into 1 by 2 square minus 1 by n square, where lambda is the wavelength, r is a constant called the Rydberg constant, and n may have integral values 3, 4, 5, etc. The value of r is 1.097 into 10 to the power 7 meter raised to minus 1. This equation is also called Balmer formula. In this equation, take n is equal to 3. We obtains the wavelength of the H alpha line. 1 by lambda is equal to 1.097 into 10 raised to 7 into 1 by 2 square minus 1 by 3 square meter raised to minus 1. This in turn is equal to 1.522 into 10 to the power 6 meter raised to minus 1. This reciprocal of this value gives the value of lambda, that is equal to 656.3 nanometer. For n is equal to 4, one obtains the value wavelength of H beta line, etc. For n is equal to infinity, one obtains the limit of this series at lambda is equal to 364.6 nanometer. This is the shortest wavelength in Balmer series. Beyond this limit, no further distinct lines appears. Instead, only a faint continuous spectrum is seen. Other series of spectra known as Lyman, Paschen, Brackett, and Pfund series. This represented by this formula. Lyman series is equal to 1 by lambda is equal to r into 1 by 1 square minus 1 by n square, where n is equal to 2, 3, 4, etc. Paschen series is equal to 1 by lambda is equal to r into 1 by 3 square minus 1 by n square. Brackett series is equal to 1 by lambda is equal to r into 1 by 4 square minus 1 by n square, where n is equal to 5, 6, 7, etc. Pfund series is equal to 1 by lambda is equal to r into 1 by 5 square minus 1 by n square, where n is equal to 678, etc. The Lyman series is in the ultraviolet, and the Paschen and Brackett series are in the infrared region. There are only a few elements, hydrogen, singly ionized helium, and doubly ionized lithium, whose spectra can be represented by these formulas. These equations are useful as they give the wavelength that hydrogen atoms radiate or absorb. However, these results are empirical and do not give any reasoning why only certain frequencies are observed in the hydrogen spectrum.